Dun 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 dun. Prepare for the jump into hyperspace. Well, not really. We're not gonna jump into any hyperspace, and in fact, mixing Star Wars and Star Trek is never a good idea. Nobody should ever do it. So, what we're gonna do is stick some more with eigenvalues and eigenvectors, and in fact, in this class, I'm going to expand a little bit on some of the concepts that I talked about last time, and we're going to introduce a few more words, as is peculiar of linear algebra. But pretty much, we're not really going to see anything very new. We're just going to look at some ideas that we've seen before from a different perspective. So even though some of the things that we're going to look at right now may look different, they're going to have different names, but one of the things you may want to pay attention to is the fact that we're really seeing the same objects only from a different side. So let me start by reminding you of what eigenvalues and eigenvectors are. The idea is we start from a square matrix A and we look for any number lambda and non-zero vector x for which it is true that multiplying A by x has the effect of stretching the vector x by the quantity lambda. In this case, we say that lambda is an eigenvalue of A and that x is an eigenvector of A. Okay? But then we also found out that any solution of this linear homogeneous system A minus lambda I x equals 0 is also an eigenvector. That's exactly what we're looking for, with a little bit of algebra from the original definition. And of course, the set of solutions of a homogeneous linear system like this is what we call the null space of the matrix A minus lambda I. And we've seen that the null space is a vector space. It's a subspace of Euclidean vectors. So what that means is that the eigenvectors form themselves a vector space. Nothing new, it's the same null space we had before, but we're looking at it as the set of eigenvectors for the matrix A. So remember, the set of eigenvectors for A is the same thing as the null space of A minus lambda I. So we're looking at the same object, but from a slightly different perspective. And so this space is called the eigenspace of lambda for A. Okay? Or sometimes people may also say the eigenspace of A corresponding to lambda. Okay, but you can use different kinds of terminology as long as you realize that in order to have an eigenspace, you need a square matrix and you need one of its eigenvalues. Now, one interesting thing coming out of eigenspaces and eigenvalues is the concept of multiplicities. Okay. Now, remember, the eigenvalues are obtained as the solutions of the polynomial equation, called also the characteristic equation, which sets the determinant of A minus lambda I equal to 0. Okay, so this is a polynomial equation. Well, sometimes these solutions may be multiple solutions. What does it mean? It means that once we try to solve that particular equation, we find out that the same value is a solution several times, or if you want, that factoring the polynomial on the left-hand side, the characteristic polynomial, leaves some of those solutions raised, of course, lambda minus those numbers, raised to a certain power. So, for example, this polynomial on the left-hand side may end up looking like something like this. So in this case, A is a solution of the characteristic equation and is a root of the polynomial, of the characteristic polynomial, but it's such twice because lambda minus A is raised to the second power. In the same way, B is a solution, but it's raised, the lambda minus B is raised to the power 3 in the characteristic polynomial, and therefore B, we can say that it's a root 3 times. And so in these cases, we'll say that A is a solution of multiplicity 2 and B is a solution of multiplicity 3. Now, when it comes to looking at these numbers as the possible eigenvalues of a matrix, we need to add another little qualifier. We're going to say, in fact, in this situation, the algebraic multiplicity of an eigenvalue is the same thing as its multiplicity as the solution of the characteristic equation. So if the characteristic equation looks like something looks like what you have in front of you, then A will have algebraic multiplicity 2 as an eigenvalue, B will have algebraic multiplicity 3, and C will have algebraic multiplicity 1. Why do we need to add the word algebraic? Well, because there is another kind of multiplicity that we can consider, and that is the geometric multiplicity of an eigenvalue. And by this, what we mean is the dimension of its eigenspace. Remember, once we have an eigenvalue, then the set of eigenvectors corresponding to it will form an eigenspace. This eigenspace is going to be a space of Euclidean vectors, so we're going to look at what is the dimension of that eigenspace, and we're going to call that the geometric multiplicity of the eigenvalue. So last time we saw how, given an eigenvalue, we can figure out the set of all its eigenvectors, and that this set actually is the set spanned by certain vectors. And basically what we did is we found a basis for the eigenspace, and once we find a basis for the eigenspace, we can simply count how many vectors there are in it, and that will tell us the geometric multiplicity. Now, you may wonder whether we are going overboard with terminology here, and whether in fact there is no point in calling this algebraic and geometric, because maybe they're the same. Well, you can imagine that no, that's not the case, unfortunately. The algebraic and geometric multiplicity can be different. Okay, so let's have a look at that. The geometric multiplicity of an eigenvalue cannot be larger than its algebraic multiplicity, but it can be smaller. Okay, it can also be equal, of course, but it can be smaller. And in class, we're going to see some examples of a situation where, in fact, the geometric multiplicity is indeed smaller than the algebraic multiplicity. So going back to the fictional example we just were looking at, let's say that the characteristic polynomial turns out to be like this. Okay, so the algebraic multiplicity of A is 2, the algebraic multiplicity of B is 3, and the algebraic multiplicity of C is 1. So what does that do to the geometric multiplicity? Well, the geometric multiplicity of A, so that's the dimension of the eigenspace of A, cannot be any more than 2. So it can be less than 2, it can be equal to 2, but it cannot be more than 2. Similarly, the dimension of the eigenspace of B, so the geometric multiplicity of B, cannot be any greater than 3. It can be lower than 3, but not greater than 3. On the other hand, the dimension of the eigenspace of C has to be equal to 1. Okay, it cannot be any less than 1, because if it were less than 1, it would be multiplicity 0, but that would mean that 0 would be the only eigenvector. And remember, in order to have an eigenvalue, there must be a non-zero eigenvector. We're always looking for non-trivial solutions. Okay, so this is the situation that happens. Now, the proof of this fact may look simple, but then again, why not the equality? It actually requires some checking, and we're going to look a little bit more at it next time. So for now, just keep in mind that the geometric multiplicity cannot be larger than the algebraic multiplicity.